Rise. I'm gonna make the screen big and I'm gonna share the screen for notes. This might be a problem if you know what? I don't need to do the transitions. Let's just start there. Oh, sorry. I'll turn the projector on. I'm like, why aren't you writing stuff down, dude? Oh, wait, I know why. Micah, you're seeing the notes, right? Just making sure it's all good.
Yeah.
Okay. Well, just so you physics guys know, I last night I was grocery shopping, and while I'm waiting in line, I get an Instagram message from somebody who graduated a few years ago. Do you guys know who Melissa Youngsma is?
Yeah.
How
No.
You don't know, Micah?
No.
I think she's my older brother's age.
How old is he?
He is 20. He just turned 20, so she's probably 20 or 21.
Okay, so it's probably 3 years ago she graduated. That probably makes sense. Anyways, she just wanted to send me a message to thank me for grade 11 physics because she took grade 11 physics, not grade 12, and said that it helped her in her kinesiology. She said it was like a repeat of grade 11 physics. I've heard people saying first year university physics, and this is like even from the States, people have said the first year university physics is very, very similar to grade 12. So if you end up taking it, you should be well prepared. Are you good with the notes?
Yeah.
Micah, you got them all?
Yeah.
So do pay attention to this though, like a fridge magnet, 0.001 Teslas, the Earth, okay, so you won't really notice it. An MRI machine is near 7. So that's 7,000 times stronger than a fridge magnet, which is why if any of you have ever been in an MRI machine or around it, like I know my kid has gone into it and they made sure that my kid and me had 0 metal on us at all. Asked about piercings and everything because the machine will take them. Okay. Here's one of the formulas with B in it as promised from yesterday. You don't have to copy the diagram down, but it is a very important diagram. So if you don't want to leave it for a second, I'm going to go to the next slide when you're done writing this down. I'm going to go to the next slide and then I'm going to come back to this to use that diagram to explain. It's our last and most complicated right-hand rule. Can you tell me when you're done copying there, Micah? No rush.
Yeah, I'm done.
You done?
I'm done.
Okay, thank you. Okay, so we'll let you guys get the right-hand rule for a moving charge, and then we'll go back to it.
I'm done.
Thank you.
Yeah, I'm done.
All right. So this is a little bit tricky. The reason I say Z should have an FM beside it is because if it's a positive charge, Y is going, or sorry, the velocity is going this way. How do I explain this? Let me start over. First of all, X and Y. This is a regular X and Y coordinate grid. It's slanted like this, doesn't look 90 degrees because they're trying to show Z as well. By up, it means out of the page. So this is trying to show 3 dimensions here in 2. So for example, let me just, so B follows Y and V follows X. So tell me, Micah, if you have trouble seeing this board. Okay, so you can see that barely, but you can see like the Y and the X, right?
Yeah.
Okay, so the magnetic field lines, I think they were, let me check. We're going this way. So the B, the magnetic field lines were going along the Y-axis, positive this way. X-axis, that's the velocity of the charge was going. And so with a right-hand rule, in this case, thumb follows velocity, fingers follow the magnetic field lines. The Z axis is coming out of the page. If it's a positive, so if it's a proton, the force comes straight out of the page. If it's an electron, if it's negative, it goes into the page. So if the velocity was going this way, you would hold your hand this way. Field lines going this way, and then this angle, 90 degrees, so sine of 90 is pretty easy, but sometimes it'll be different. It'll have different angles and so on and so forth. But you will, like always, it's gonna be different this year because of tests and stuff, but always I'd have students in the room that get to certain questions and it's like this on the page, it's totally normal. Like that's kind of what you have to do. So know that the Z is coming straight out. So that that picture can be misleading. So this is out of the page. It says up, out of the page. The reason I said it should have FM beside it is because that is the direction of the force. If it's positive. If it's negative, it's going down into the page. We okay with this?
Yeah.
All right. I'll do a couple examples. The tricky part is the right-hand rule. The formula is a formula. Okay, everybody's good? Everybody's got it?
Yeah.
So I still would recommend going to those tutorials. I've got lots of space. That's good. Oh, goes way left. Okay, anyways, I would recommend looking at those tutorials, but I'm going to do a couple of the practice questions with you. Let's do 1 and 2, page 390. Okay, question number 1. It says a proton with a mass. Why is it giving us mass? Oh, part of the question later. Okay, I don't care about that. Is moving horizontally eastward. Okay, so for 1, it's a proton. So the charge is 1.602 times 10 to the negative 19. Can you see that? Can you see that okay, Micah?
Yeah, it's okay.
Okay, I'll say everything I'm writing down too, so that you can pick it up that way too. Okay, so the charge is 1.602 times 10 to the negative 19. The velocity is 9.4 times 10 to the 4. 9.4 times 10 to the 4. Now the direction is uber important. Horizontally eastward, so that's to our right. Okay, so I'm just drawing that so I can keep track of it. Magnetic field strength 1.8 T. B equals 1.8 T, and it says it's directed upwards. Now up, based on what it said before, up is in like the Z plane. Okay, so up isn't north. It would say north. Like this is east. Up. So what do we got to do here? Calculate the magnitude direction of the magnetic force. Okay, so our formula F equals Q V B sine of theta. So we're just plugging stuff in. This is the easy part. Q is 1.602 times 10 to the negative 19. Q V. V is 9.4 times 10 to the 4. B is 1.8. Sine of theta, so it's sine of 90, which is 1.
Is it always going to be sine of 90?
Nope. It'll give you the angle though. So it'll still be, you just got to plug it in. Like I said, the trickiest part is figuring out the orientation. So we just got to multiply all that. Yeah, I'll let you guys multiply just to make sure it gives me the right answer.
.71 times 10 to the negative 40.
Cool. No, it's good. I just
It's
don't
on the page.
Yeah, no, but still, I want to.
Yeah.
It's still good to make sure that it's doing what it should be doing. But now the direction, what we need here. So we're told that the current is going east. So the thumb is going that way. Who knows what my hand's gonna do after, but the thumb's going that way. The magnetic field lines are going up, not north, which is up is basically towards us. So it's towards us. And so it is a is it positive? Is it a proton? Yeah, it's positive. So then it is going to go south. It's coming out of our palm south. Is that my orientation is goofy, but velocity is going that way. Field lines are coming out of the page. So this is like, this is the page. So this is going south. Positive. Remember I said it's weird. Is that making sense or? Yeah, honestly, the big difference is keeping up and down or out of the page into the page separate from north and south. So like a piece of paper in front of me. So I would go, and I'm mirrored to you, well, to both of you. My thumb is going to the right. Same, like, so your right would be the other way. My thumb is going that way. The field lines are coming out of the page. So it's like my hand, it's like a model of a hand sitting on like a desk on a piece of paper. It's positive, so it comes straight out of the palm. So it's going down the page. It's so weird. Does that make some sense?
Yeah, sort of, yeah.
Micah, is that somewhat sensical?
Yeah, what if it was an electron? Would it be going north? Like, does it go at the back of the hand?
Yeah, they go out of the back of your hand. Exactly. If it's negative, opposite direction. Yeah.
Okay.
Okay.
Yeah.
Okay, you good-ish for now?
Yeah.
Okay, so 1B, it says determine the gravitational force on the proton. That's just F equals ma. And determine the ratio of the gravitational force to the magnetic force. So the only reason it's asking you to do this, like you should know how to do it. It's very straightforward. That's why I'm not going to do it. But the interesting part is notice the magnetic force compared to gravitational force. The gravitational force is 6 times 10 to the negative 13 times less. So the magnetic force is insanely strong compared to gravity. That's all it's really saying there. So 2, let's look at 2 is a little bit different. Can I erase the board?
Yeah.
Micah,
Yep.
is that okay that I'm skipping 1, B, and C? You guys okay with that?
Yeah.
Yep.
So number 2 says, determine the magnitude and direction of the magnetic field. Okay, so we need to get B. We don't know what B is. An electron, so it's an electron, so the charge is negative 1.602 times 10 to the negative 19. 3.5 times 10 to the 5, so its velocity is 3.5 times 10 to the positive 5? Yeah. That'd be really slow electron otherwise. Now it says it's moving upward. Upward is out of the page. Okay, so up or out of the page. It's weird because when I'm writing on the board, it's not up. It's kind of coming horizontal. It's different. Think of it on the page. The force, F equals 7.5 times 10 to the negative 14, and it's to the right, which is east. Also remember, this is an electron, so we'll figure out the math of it first, but it's the force is going to be coming out of the back of our hand. So I'll do that when we get to it. Okay, so F equals QVB sine of theta. Force is 7.5 times 10 to the negative 14, excuse me, equals Q, which is negative 1.602 times 10 to the negative 19. Q V, the velocity is 3.5 times 10 to 5. QVB, B we don't know. So that's left blank. Sine of theta, and again, this one is 90. It's kind of funny how I'm talking loud to make sure Micah can hear me. If somebody were to walk by, just Gavin in the room. And then what you do here, okay, so we divide this by everything else, which please feel free to punch that into calculator just to make sure I'm not making a mistake. B,
I have a question.
Yes.
For a second.
Yep.
If theta is the angle between V and B, and you don't know B, how do you know it's 90 degrees?
Yeah, you know what, I'm kind of assuming unless it says, but what you can do is we can figure that out. I was thinking about that as soon as I started doing this. What we can do is we can think that, so yeah, we don't know the field lines, but we know that the velocity is coming up. So your thumb is coming up, like it's sitting on the paper in front of you, it's coming up. The force is going to the right. So it means that your magnetic field lines are going to have to go in the positive Y direction.
Okay.
Does that make sense?
Yeah.
So that, and so then that would tell you the 90 degree. I did it because I knew that like it tells you when it's a different angle. But that's a good question. Thank you for that. So B is 1.3 Teslas. And it's telling me it's in a different direction. So let me have another look at this. Horizontal, comma into the page. Well, so if up, unless it's making a mistake and because that's up. So if like the page is my hand, that's up. The comes out of the back of my hand to the right. The magnetic field lines have to be going north. Why does it have it into the page? See, the only way it could be into the page, the way the book has it, is if up is north. And I think there are places in the book where it mistakes the two. Do you know what I mean? Up for north, which is not good. Do know that on a test I will be exceedingly clear. And if for some reason I did this and you guys got the answer that we're getting, and I had a different, you will be right. Does that make sense? Like this is misleading. I think they've mixed up the up and the north, which is easy to do. You guys know what I'm saying?
Yeah,
Yeah.
Like, so X is V, B is Y, and force is Z, right?
Not necessarily.
Okay.
Because you could have, so like if we have, this is north, south, whatever, west, east. And then so, sorry, that is not what I wanted to write actually. This is Y, the vertical is Y, the horizontal is X.
Yeah.
You could have the force going in the positive Y direction, which means that's the back of your hand. And then if you just need, it's like the three things, it's the force, the field lines, and the velocity. If you have two, you know the other one. So you could be told that, what did I say is going up? The force?
Yeah.
So you could be told that the force is going up and the velocity is going into the page.
Yeah.
Which means I gotta go this way. So the thumb is negative Z, the force is positive Y. If it's negative, because that's the back of my hand, if it's negative. If it's a positive, it's like this.
Yeah.
Okay, you see where I'm going with this? And then, so then the lines have to be going in that direction. But that's what I mean, like test time, people are like doing weird things. Are you okay with that, Micah?
Yeah.
Okay, any other questions? From either of you? All right, that's it. See you tomorrow.
See ya.